So yeah, it's a pleasure to speak here. And this what I'm going to talk about is joint work with one of my collaborators on Zoom. So joint work with Shrikant Iyengar. The title is the numerical criterion of call it Wiles-Diamond. So this was the criterion which showed up in a prominent way in Andrew Wiles' work on Fermat last year. So Andrew Wiles this is the venue in which he proved his great theorem. Maybe I can assume all of you know modularity defect, but I'm not going to do that. I'm going to start from scratch. Maybe I'm going to spend too much time perhaps in the background, but okay, tell me if I'm going too slow. All right, so of course the work of Wiles has been a great inspiration for.
Hey, maybe he's on the Zoom.
Oh, he is?
I should have. No. No, that's easy.
I, for example, am very inspired by his work. I keep on looking at his paper and the various parts of it which inspire one to do kind of follow up on various of his ideas. For example, some motivation for this work comes from chapter 3 of his work on Fermat last year, which is something about killing Selmer groups using level raising arguments. All right. So this work, I mean, in some sense, we've been pursuing this for many years. So this particular work is with Shrikant and Jeff, but earlier I've collaborated with Gebhard Bokler and Sylvain Brochard. So this is kind of an ongoing work in which we were trying to understand Wiles' numerical criterion. So first, let me begin at the beginning and go back to 1994-95 when Andrew Wiles proved Fermat last year. So starting with the counterexample to Fermat. I'm not going to be very precise, but okay. So suppose you want to prove Fermat, right? So you start with something which is a counterexample. You suitably normalize this pair ABC not equal to 0, co-prime, right? And then Fry, you want to show that you get a counterexample, assuming that Fermat last theorem is false. Then you can consider this Fry elliptic curve, y squared equal to x into x minus AP into x plus b. Right? So Fry has this intuition that perhaps this elliptic curve should not exist. I mean, of course, it should not exist if Fermat last theorem is supposed to be true. So the falsity should lead to a contradiction. So this elliptic curve should have some contradictory properties. And the contradiction comes from kind of studying in some sense closely the ramification of Galois representations arising from this object. Right. So starting with this. So this E. So let's call this elliptic curve E. So E is if you suitably massage ABC, right? I'm not going to go into the yoga of that, but so E is semi-stable with the right choice of ABC, with the right way of permuting it around. And it's Fry observed that it will be, or Fry kind of guessed and maybe say made precise, the mechanism whereby you can derive a contradiction from such a curve existing if you assume the Shimura-Taniyama conjecture, right? So some of our the contradiction was that E is semi-stable, okay, and the Fry observed that E is semi-stable, okay, and so the Shimura-Taniyama conjecture, or the modularity conjecture, is that this elliptical E should be covered by modular x naught n, and where n is the conductor of the elliptic. Right, so far there's no contradiction because this elliptic curve in fact has fairly large conductor. Right, so the conductor of this elliptic curve n is equal to the radical of ABC. Right, so no problem. You could have a very large solution to Fermat last theorem. This elliptic curve would have a large conductor, and there's no reason why x naught n there could not be a Cus form with giving rise to such an E. Right, so the contradiction came from considering the mod P representation associated to this elliptic curve. So what you consider is you look at this the P torsion of this elliptic curve. And this has an action because this elliptic curve is defined over Q. This is an action of the absolute Galois group of Q. And from this, you get a representation, a mod P representation, rho bar EP from GQ to GL to FP. Right? And one can assume P is large enough. Okay, again, I'm going to be pretty loose about all this kind of stuff. Okay, but P large enough, this Galois representation by results of measure will be irreducible. 7 or something, I don't know. Right. So this representation is irreducible. It's odd in the sense that the determinant of complex conjugation is -1. And the contradiction, which kind of, maybe flies intuitively sense and then say made precise, is that this elliptic, though this elliptic curve has bad reduction at many primes, this mod P representation is almost everywhere unramified. Right. So in particular, this representation, because the discriminant of this elliptic curve, right? So the conductor is whatever it is, but the discriminant is also very large, of course. But it is kind of a pth power, essentially, right? It's something like 10 to the -8 ABC to the 2p or something like that. Right? So again, something very large, right? But the key thing is that the exponent, that most prime numbers, besides 2, are dividing this discriminant with valuation with kind of exponent divisible by p, right? So from this, one can easily check using Tate uniformization and kind of stuff like that, that this mod p representation is kind of has a very limited ramification. Right, so the Serre weight, which is something measuring the ramification at P, is equal to 2. And so also the level of the Artin conductor of this representation is 2. Right? And so then one expects, the Serre conjecture, that this representation comes from the space of modular forms of weight 2 and level 2. Serre. Right, and then the space is 0. So this would be the contradiction you seek for from Fermat's last theorem, right? And so, but to make this transition from modularity of Shimura-Taniyama to getting a contradiction this way, you needed this epsilon conjecture. You needed to know that this thing, so Ribbit proved that if E is modular, so this is a conjecture. I mean, some form. So it's an epsilon conjecture, anyway, some form of it. And then Ribbit showed that if E is modular, if E is modular, then he proved this epsilon conjecture. Then Robar. Right, so Ribbit can do this level, celebrated paper level lowering. Right, again, which I've spent many months reading and not understanding as a graduate student. So all these things which I study as a graduate student kind of have been inspiring for me. Okay, and okay, but on the other hand, how does one verify this, right? So that's where Wiles-Diamond is kind of epoch-making work. So he produced a technique to show that he is modular. And rather than thinking of this geometric object, he just looked at its Galois theoretic incarnation. He looked at an elliptic representation arising from it. So choose a prime L. Anyway, there's some art in choosing which prime, right? But to begin with, you can choose any prime. If you choose a prime L, instead of considering E, you can consider its elliptic representation. Right? And but because of the results of faulting, it was enough to show, to prove Shimura-Taniyama, it was enough to show that this Galois theoretic object, in fact, came from the modular world, right? So because of faultings, isogeny theorem, enough to show that rho EL is the Galois representation associated to some new form of the right level weight, right? Where F is some new form of weight 2 and level this conductor N. Right? So this is the new form. So that was the statement Wiles attacked, right? And for that, he invented this technique called modularity lifting. Right? So this is the thing I want to talk about. So the modularity lifting technique. So the modularity lifting technique is where you want to prove this is modular, but you have to start somewhere. Right? So you give yourself the information that the residual representation is modular. Right? So this is the kind of the Wiles and 1994, 95. Okay. So the basic idea is that you say that you look at this scalar, look at some representation, you want to show its modular, right? Or you can just call it rho. And you want to say it comes from a new form. What you do, what you give yourself is you assume it's residual representation. First of all, it's a large image. So assume it has kind of large image, whatever, for example, irreducible. And it is modular. From some modular form, maybe not the same. I mean, from some new form. Right, so assume you kind of size conjecture for the characteristic L representation, and then the modularity lifting technique is that we are bootstrapping from the mod L statement to the L-adic statement. Right, so that was the modularity lifting kind of in technique Wiles invented, right? Wiles and Taylor Wiles. Okay, so how does one start? Right, so you can apply this to you're given this representation you're interested in. You can apply this to for L equal to P. Suppose you chose the prime L equal to P. Of course, then there's a problem because then the thing you want to prove is what you're assuming, right? You want to prove that rho bar EP is modular in this strategy. Assumption that rho bar EP is modular is not good. Leads to some circularity, right? Or this rho bar. Yeah. This rho could be a rho EL, right? So if you look at the prime L equal to P, then assumption is then introduces some circularity in the argument to prove Fermat's last theorem. Right. On the other hand, in work with my French colleague Jean-Pierre, we proved size conjecture, but we actually can work. Now this is now racing up 10 years ahead or something. We can work with this using these techniques invented by Wiles and developments. You can in fact now work with this P, right? So this is work of in fact, Tate, apparently I've heard from some people that Tate had suggested the strategy of proving Fermat's last theorem is to show that that instead of going via this route, you can just try to show that rho bar somehow arises from some object which does not exist, right? It should arise from an abelian variety of a suitable sort, right? So one prove that instead of choosing this lift, instead of looking at the p-adic lift coming from E, you can try to produce a better lift which is adapted to the ramification properties of the residual representation rho bar EP. Right? So we proved that starting with this rho bar EP, I can write here, that's fine. Yeah.
Saying what a great system we have.
So what we did is we produced a lifting, right? So this kind of feedback. Okay? So we produce a lifting to some kind of characteristic zero representation. It will not be this thing coming from E because that is a lot of ramification, but we produce the best possible lifting in terms of ramification properties. Right? We produce this lifting, which is geometric in the sense, which is geometric, okay? So it's unramified at almost all primes, and it is good in the sense of Fontaine at P, but a bit more, we show that this representation has that this lifting rho, let me call it rho twiddle or something. Rho twiddle has conductor 2 and weight 2 in the sense it's crystalline of its Varsity-Tate at P. Right. So instead of you start with E, then look at rho bar EP, but instead of now you exit using a different representation. Right. You exit you can create this representation off ramp. Okay. This rho twiddle, and now this rho twiddle, in fact, you show. Now, this is a characteristic zero object, a p-adic representation with very limited ramification, unramified outside 2 and P, and it has kind of unipotent ramification at 2, and it is kind of good reduction at 2 at P. So, in some sense, the intuition is that maybe one can try and show that such a thing doesn't exist. And you also show, in the course of proving this uses this potential modularity developments of Taylor and other things. Okay, you show that this rho twiddle, in fact, also arises from an abelian variety. So, maybe I should switch here. Any questions so far? All right. What you show is that row twiddle, in fact, is a Galois representation. You can there are a couple of different ways of finishing this argument, but one way of doing it is to show that it arises from an abelian variety, but not different from E, arises from a semi-stable abelian variety A over, let's say, Q, semi-stable, good reduction outside 2. Right, so that somehow our work gives a rearranged proof of Fermat's theorem, but of course it relies upon the techniques of Wiles. Semi-stable with good reduction outside 2. Right, and such a thing then Fontaine had proven doesn't. Fontaine and Brushkin had shown that such a thing doesn't exist. Right? Or
this A is coming through this potential modularity, or
yeah.
So that can be quite big.
Sorry,
the number field.
No, but this is over Q. Yeah. Somehow you do some
sorry, but the actual A might have big dimension.
Yeah, but somehow the point is to descend somehow. Yeah. So from a reduction outside too. I mean, the abelian variety is just a crutch. You can just say that row twiddle propagates to a compatible system, and then Fontaine and Brushkin prove that such a is 0, which is a contradiction. Right, so that is the kind of argument you could do if you kind of most naively just work with P, right? L equal to P, which of course wasn't available when Wiles.
Of course, that doesn't. Their proof doesn't use modularity.
Yeah, so this is without referring explicitly to modular forms, but yeah, this is Tate's strategy apparently. Tate had suggested that one could try and do this, right? Rather than though rho bar comes from this elliptic curve, which has lots of bad reduction, make it come from another thing, which of course will not necessarily be an elliptic curve. It might be a higher dimensional abelian variety, but still of GL2 type. Oh yeah, it doesn't matter. You can just show it comes from some abelian variety, right? As long as it has this good reduction property. Okay, so that was not what Wiles did, right? So to apply modularity lifting, what Wiles did was we looked at L equal to 3, right? So that was kind of okay. I'm taking a long time to arrive at the point, right? Which I'm gonna, but it's okay. I thought maybe the audience.
Most of the people here weren't there.
Yeah. Okay, so what is the advantage of L equal to 3? The point is that somehow the residual representation. Because this representation, for example, if you look at this GL2FP, right? I mean, P will be a large prime because Fermat is known for lots of primes even before Wiles. We will be working with some horrendously large prime. This will be a horrendously large representation. Can't do much with it, right? With this assumption of residual modularity. On the other hand, if you work with L equal to 3, right? Then you have, then you look at rho E3, the triadic representation. And there somehow you're in luck in terms of, you reduce this representation mod 3, then the representation is small image. Right. So somehow, I mean, again, there are a couple of steps in this. I mean, first you assume that this representation has large image, right? And then there's this famous 3-5 trick, which allows you to get around that. So now the advantage is that that GL2F3 is a solvable group, right? It's a double cover of S4, right? Solvable in particular. Right, so you can apply Langland's tunnel to satisfy this assumption that the residual representation is modular.
I mean, there's a funny thing there that people don't often point out, that the Langland's tunnel used the converse theorem on GL3. And when they introduced the converse theorem, which then would solve this problem, but the converse theorem was used in the first proof, but on GL3 through Langland's tunnel. That's a tunnel part.
Yeah. So in fact, this is one advantage of this proof. This proof does not make use of Langland's tunnel. It certainly makes use of base change, solvable base change, but no extras, no Langland's tunnel. I mean, this proof is outlined there. But certainly, Wiles, for example, that means it used Langland's tunnel. And now, so here it's by Langland's tunnel, then this because of the smallness of this representation. So let me, as a first step, assume this representation is surjective or something, right? And then there's this 3-5 trick. Okay, then the Langland's tunnel would show that rho bar E3 is modular. And then modularity lifting will take over and prove the statement you want. Right? Because in the faulting statement, you can work, but you take advantage of the fact that the prime L you work with is up to you. It is up to you. Okay, so Langland's tunnel will show that rho bar E3 is modular. And then and of course the main thing, the main kind of weightlifting part of the argument is to prove this implication is that rho E3. Right, but if you read the introduction to Wiles' paper, he said even this realization that you work with L equal to 3 is it occurred to him after some time, right? First he was working with L equal to 2. So even though this now seems natural to do when you're doing things for the first time, things take longer. Okay. All right. So yeah, and then if this assumption is not satisfied, then there's a 3-5 trick which I won't go into, right? Just to so that I'll actually talk about something I've done, which we have done with my lab. But then there's also a 3-5 trick. Okay, so therefore modularity lifting is what I want to think about, right? What I want to talk about. And there it occurred in 2 steps. Right? There was a minimal case and the non-minimal case, right? So there was a strategy, which in fact was the strategy I started with, which was this numerical criterion, right? And which went some distance with which he could not complete the argument. And then there was a patching step, right? Which kind of complemented that and completed the argument. The patching was done with Taylor. All right, so now let me actually talk about modularity. So this finishes one part of my talk. So any questions at this point?
So you want okay, in a high, maybe I should wait. You're going to talk in higher dimensions.
No, I'm going to talk about. I'm just going to talk about.
So you're trying to prove a new modularity theorem, or are you trying to address other Diophantine equations? What's the aim?
No, modularity lifting. Yeah. Okay. I want to. So modularity. Wiles' work at 2 strands. Modularity lifting. Sorry, modularity lifting at 2 strands, 2 steps to the argument. One was patching, which has been generalized extensively, about which I have nothing to say except that we use it. And the second thing is the numerical criterion, which somehow has not been developed. Right? So I've been interested in the numerical criterion, and in this work with Jeff and Shrikant, we kind of actually have a generalization beyond the situation of Wiles. So the application in the end, which of course many of my talks somehow don't have application. I'm going to tell you the method. The application in the end is to prove some. So let me tell you that because I won't be not saying the theorem. The application in the end is to give a way to produce to prove non-minimal modularity lifting theorems. For those who know what that means, non-minimal R equal to T theorems integrally without inverting the prime P, which somehow are especially interesting in the case when you're dealing with rather than the cohomology of the modular curve, you're dealing with cohomology of some hyperbolic, what is it called, Bianchi manifold, which has a lot of torsion. So when you invert P, you kill that. So we want to work without killing torsion. That's one outcome of this. But what I'm actually interested in more is just developing the numerical criteria. Right? This is also an application, but I think there should be other applications. Okay. Okay, so as I said, the modularity lifting theory, first of all, the grammar of Wiles' proof is the language of deformation theory, right? Or kind of so somehow rather than proving statements pointwise for this given Galois representation, you put it into a family, and then kind of somehow, of course, once you have a deformation and some parameters, you can specialize at different points and play tricks, right? So somehow the statement is kind of you're interested in is about characteristic 0 representations. Right? Somehow kind of you do it via improving something finer, right? Okay. And anyway, this entire game is about proving something finer, right? Because the classical Lagrange program, it doesn't deal with integral theory, right? So that's one of the great triumphs of this kind of mathematics is that very fine stuff about congruences between modular form has proven one of principal statements of, statements which are viewed as part of the Lagrange program, right? Of course, Shimura may have predated Lagrange. Yeah. All right. So modularity, so it's important to get fine integral statements, right? And so this is again. Though part of that same philosophy. All right, modularity lifting occurred in 2 steps, 2 stages, or 2 steps. Okay. And to be a kind of to put them in the inverse order to in which they were discovered, right? The first thing is the one step is patching, right, which occurred later. But the original argument of Wiles was based on this numerical criteria. Right, so this somehow proves kind of modularity lifting in the minimal case. Originally, minimally ramified case. And the second thing is the numerical criteria. Okay, so this is to deduce from the minimal case the non-minimal case. Let me just do this. Right, and both arguments kind of rely upon innovations in commutative algebra, but motivated, right? Motivated commutative algebra, motivated by number theory. So I want to, so even the kind of one of the main things we are going to do is do some new commutative algebra, right? Which then has some dividends for R equal to T. So develop the numerical criterion of Wiles and then Diamond to higher dimension. Yeah. Okay. So now, so how should I do it? I mean, so let me tell you briefly about patching. Of course, I mean, all this kind of does take time to set up properly. So it's more like I can tell you roughly what the basic setup is rather than giving any details. So the deformation theoretic statement one proves is identifies two rings, one which parameterizes Galois representation and one which parameterizes some kind of modular forms. Right, and you prove the identity of them and then deduce Shimura-Tanya. Okay, so let me do the patching. So let's do the minimal case. Okay, actually, maybe I'll just do because I think I've spent a lot of time on the introduction. So maybe I should come to the part where let me just minimal case. So the minimal cases. So you have some kind of minimal deformation ring. I'm going to call IR phi. Right, kind of its points will parameterize. Right, so somehow you have some object rho bar you're interested in deforming, like this rho bar E3 or something, into some finite field, right? A finite field characteristic, let's say L. Like L equal to 3. Okay, so you have some minimal deformation ring whose points, for example, correspond to minimal deformations of rho bar, right, with the same kind of inductor or something. Right? So this, and on the other hand, because so rho bar you assume it comes from a modular form. Right. So just to give some sort of flavor of what this means is that this means that if you consider a cohomology of the modular curve of some suitable level adapted to rho bar, right? Something like the Artin conductor of rho bar, and I'm assuming the Serre weight is 2 or something. Right, you consider this kind of cohomology group, whatever flavor you want, Betty, better all of this modular curve, and this has an action of the Hecke algebra. Right, this has an action of the Hecke algebra, and the fact that you're assuming this is modular means that somehow it arises from this world of modular forms, right? So there's a maximal ideal of this Hecke algebra, and then you localize this thing, okay? And the residual representation. So rho bar is actually isomorphic to is equal to rho bar M, which is some residual Galois representation associated with GL2 with values in the residue field at M. Right. So that's the setup. And so okay, and because we assume that rho bar is large enough image. Right, and by theorem of Khare or something, or some kind of integral refinement of Eichler-Shimura, you have a kind of universal modular representation GL2 of G cube into GL2 of the Hecke algebra, right, which glues together the Eichler-Shimura representations associated to the new forms coming from this, contributing to this cohomology, right, by the Matsushita. Okay, and okay, so I'm going to call this maybe T phi just to match with the notation. Right. And there's a natural map because the universality of this Galois representation, there's also a universal Galois representation into GL2 of R. Right. So there's some surjective map R phi to T phi. Right. And then the modularity lifting you want to prove is you want to prove that this is an isomorphism, right? This map is injective. Okay. So how does one do that? Of course, this is like impossible to do, right? If you just stare at it, because you're just given two inert objects. I mean, you have to move that, right? So kind of this is, so you use kind of this argument, which number theorists have often resorted to, right, from Shepard-Truck's proof of his density theorem, Artin's proof of his reciprocity law. You introduce auxiliary ramification, right, into the picture. So what went up, what Wiles did was, it's impossible. We're just given a map from two rings. I mean, there's one situation in which you could perhaps prove that they are equal without any work, was if it happened to be that R5 is just, let's say, O itself, right? But there would be some very, if R phi itself was a smooth object of some kind, you could perhaps hope to just look at it through it. But in general, this R phi is, I mean, it's kind of a complicated thing. Or rather, T is also pretty complicated. So when you tensor, again, this is some integral phenomena. If you tensor it with QL, it becomes very simple. But integrally, it's rather complicated. Okay, that's kind of draw a picture. It's kind of a series of, it's some kind of very complicated kind of thing. Okay, so it's very difficult to just work with it itself. So the idea of patching is to introduce auxiliary primes. Okay, now to cut a long story short, now this, let me call this module M phi, right? So what one wants to do in patching is that you have module R phi, the ring R phi, which acts upon a module M phi, and somehow you just want to prove that this action is faithful, right? You want to be, if you prove this action is faithful, because the action of the Galois deformation ring on the Hecker module factors to the Hecker algebra, you'll get R equal to T, right? Instead, you manufacture by some kind of pretty intricate process some module M infinity and a ring R infinity, right? On which acts upon this, and somehow sitting inside the S R infinity is some power series ring S infinity, right? Which is a power series ring in a certain number of variables called S1 up to SR, right? Which somehow comes geometrically from some sort of action of some diamond operators, some kind of the simplest part maybe of things acting upon the modular curve, but somehow they're made to carry all the weight. Okay, and on the other hand, somehow the situation is okay. It's also a quotient of a power series. Right? So O is some dVr if you're fixing. So it's also a quotient of x1 up to xg. G stands for generators, R for relations, right? And the situation is that the depth of M, that M infinity is a free S infinity module. So in particular, the depth of M infinity as an S infinity module is equal to the dimension of S infinity, right? Which is equal to G plus 1 of R plus 1. Right? And on the other hand, if you stare at this, because now the numerical coincidence, right? The numerical coincidence is, so this is the magic, some balancing act, right? The numerical coincidence, which is different from the numerical criterion, okay, is that G is equal to R. Right. So from this, we stare at this because then G is equal to R, the upper bound and the dimension of this R infinity, right? And somehow you go from this infinity picture, you descend down by going modulo the variables S1 up to SR. Right. So the descent is go modulo S1 up to SR. Right, so of course, those who have not seen this probably doesn't make sense, but I'm just giving you the algebraic picture, right? You do some kind of work in Galois cohomology and work in modular forms to kind of realize this picture. So what you get is that the depth of M infinity is equal to the dimension of the thing, and on the other hand, this is certainly less because the S infinity action factors to R infinity. This is equal to the depth of R infinity. Right, so you basically get that from this you conclude that M infinity is maximal Cohen-Macaulay over R infinity. And then you can apply to M infinity over R infinity the Auslander-Buchsbaum theorem, right? You can so using the Auslander-Buchsbaum theorem, which tells you that there's a connection between the depth and the projective dimension and the dimension of the ring, right? So using get implies by Auslander-Buchsbaum. That M infinity is a free R infinity module using this numerical coincidence. And this implies the thing, but this thing is some artificially constructed. This has no relation to reality in some sense. This doesn't really correspond either to space of modular forms or this, or even some inverse limiters, right? But you descend down to the thing you're actually interested in, and you get that R phi acts freely upon M phi. I mean, M phi is a free T phi module, R phi module. And which implies R phi equal to T phi. And at the same time, you get that all these things are finite flat complete intersections, right? Because this M phi is a finite flat O module, right? It turns out that these SIs give a regular sequence, and this thing presents R phi as a complete intersection, right? Okay, so this was in a nutshell the patching argument. That's just the axiomatics, I mean, the algebra of it. Right. Okay. On the other hand, what happens to the second stage? So somehow this argument works best in the minimal case when you allow ramification of in the Alaric representations, which is no more than in the mod L representation, right? Because somehow if you want a power series projecting onto this with the right number of variables, somehow you play this balancing game. It's best to have minimal ramification, right? But so in the second step, which in some sense preceded the first step. So in this numerical criterion, Wiles used a different argument, maybe partly inspired by Hida's formulas for interpreting adjoint L values, special values of adjoint L functions associated to F in terms of congruence modules. So the numerical criterion, what is it? So now the game is that somehow you have an R equal to T theorem with minimal ramification, and you want to relax the ramification condition. And so you want to go from a level like n phi to some higher level and still preserve R equal to T. So the numerical criterion. Okay, now this part of the argument, right, has been generalized by Calegari-Geraghty to some more general situation where this numerical coincidence may not happen, right? Well, our goal is to generalize this numerical criterion, which I'm going to talk about. So that will apply also in this Calegari-Geraghty, this positive defect situation. Okay, here also somehow now you want to change the level from, let's say, n phi to, let's say, something like n sigma, where sigma is going to be some set of primes at which you are allowing ramification, which are beyond the primes which ramify and rho bar, right? And similarly, so you're enlarging your deformation ring from r phi to r sigma, and it's going to act upon some module m sigma, right? Which will typically be the cohomology of some modular curve of some higher level n sigma, right? Which will be divisible by n phi. Yeah, and again, you want to prove that this action is a free action. You just actually care about faithfulness. You just want R equal to T, but actually what you get is that M sigma is a free R sigma module and R sigma is a complete intersection. Right? You always get more than you ask for. Okay, so R sigma, you want to prove this. Okay, so R sigma is moduli space of Galois representation with some ramification at a larger set of prime sigma. So you want to prove the freeness of this action. Right? Somehow the way patching initially worked, it could not handle the case of greater ramification. Later Kissen did modify it to. So what is the strategy here? The strategy here is to verify that two numbers are equal, right? So somehow measure measure the situation by attaching two numbers to these things, right? So the Selma group and the congruence module or congruence number, and showing that these things have the same order, the congruence module and the Selma group. Okay. So let me. So now we have somehow R phi acting faithfully now on M phi with all these extra properties, and you want to deduce. So here you know that this action is free and R sigma is a complete intersection, R phi is a complete intersection. And you want to deduce the same thing for this, right? You want to deduce that this is this acts freely and R sigma is a complete intersection, finite flat complete intersection. Right? You want to somehow have some mechanism of going from here to here. And for that, first of all, you kind of Wiles develop this criterion, which was then improved by Lenstra. So this is pure commutative algebra, and then you apply it. Of course, then you have to fulfill the conditions which. Okay, let me say the commutative algebra criteria. So the situation here is, so this is some commutative algebra. And one of the main pieces of our work is to generalize this thing to higher dimensions. Right, so what is the situation? So you have some kind of R, which is some complete Noetherian local coalgebra, right? And you have an augmentation. So in the patching argument of Y, any particular modular form did not play a particular role, right? You just work with the residual representation. But while here you kind of really work with the modular form. Okay, so that in terms of the commutative algebra translates into fixing an augmentation, a map from R to O. Right, so imagine this coming from a modular form. Okay, and then the key assumption on this thing is that the cotangent space of this, right? So phi lambda, which is equal to kernel of lambda upon kernel of lambda squared, right, is finite. Assume finite. That finite will be zero. It's a finitely generated O module for free, right? But you force it to be, you assume it to be a finite obligate. Right, so that's the situation. On the other hand, now that's the deformation ring or the Hecker ring part of it. But on the other hand, you need a module. So now you assume that you have a M, you have something which is finite, a module M finite, R module M, which is finite, well, basically of positive depth, right? But basically you may assume that it's finite flat over rho. Okay, so that's the data of the ring. The data of the module is let M be an R module, finitely generated. Right. So note that this condition could also be translated as saying that if you localize this ring at the let me call kernel of lambda equal to prime ideal. So this is basically the condition that P lambda is a minimal prime ideal, right? And the kind of R mod, that thing is O, right? So there's a component of this ring which is finite flat over O, right? So this could be retranslated, reset as RP lambda is equal to K, the fraction field of O. So that's a small exercise, okay? Anyway, so you have this, and okay, now the other thing is that I'm just writing it this way to state my generalization later. Okay, so now M is a finitely generated R module, okay? And you assume something, for example, Diamond would assume it's finite flat over O, but what is enough is to assume it's a positive depth. Right? Some of the depth condition is very important, especially for our later work, for our work, right? Okay, or for example, certainly with assuming finite flat over O would imply it. Okay, so assume it's a positive depth, and now you assume that M is this M is supported at lambda, right? So you assume that M localized at P lambda is non-zero, and then you record its rank, right? Suppose this is isomorphic to K to the D for some D bigger than 0, right? Which is to say that lambda is supported by M, right? And then Wiles kind of Diamond, they measure two numbers attached to the situation. One is the order of this group, right? And the other is this more subtle thing, maybe, which is the congruence module of lambda, which occurred in the work of Hida and maybe other works as well. Okay, so the congruence module. So there are two invariants we are going to focus on, or Wiles focused on in Diamond. So this is phi lambda and the order of it. The structure of it as an abelian group doesn't matter so much in this criterion, okay? And the other invariant is the congruence module of lambda, which is measures in some ways congruences between lambda and other augmentations, not lambda. Okay. So I have to define this. So there's something called the congruence module of lambda, right? Which Wiles discovered in practical situations like M coming from the comodular curve. The congruence module is something which is related to L values, right? So congruence module is psi lambda M. So what is this? Right? This is now again to motivate by I'm setting this up so that I can tell you our generalization. Okay, so this this is the co-kernel of the following map. Right? It is the co-kernel of the following map. Okay. So you go from HOM O to M as everything is R modules. Of course, O is viewed as R mod P lambda, right? So O is viewed as an R module via this augmentation lambda from R to O. Okay, so it goes from HOM OM to HOM. So now this way, if you think about it, this is just the part of M which is killed by the kernel of lambda. Right? And on the other hand, you go to HOM R to O M tensor O. O lambda, right? And of course, another way of writing this is just equal to HOM. I'm writing it in an unnecessarily complicated way to define the right object later. Okay, because I'm going to interpret these HOMs as x0. I want to talk about higher x. Okay, so HOM R from O to, of course, is just equal to M tensor O lambda, but okay. So but HOM M mod P lambda M, right? This is what it is by definition. Okay, but this turns out to be not the right object, right? You have to pass to that. So this might have torsion. So you pass to the torsion-free quotient of this. Right, so this is going to the free part of this. So torsion-free quotient. It turns out to be torsion-free quotient. Okay, and what is this torsion-free quotient? It turns out to be m modulo m tilde by the annihilator of P lambda in the ring R. Right? So this entire congruence module is just the co-kernel of this map from here to here. Right? So it's of course right, psi lambda m is just equal to m modulo these things. In some sense, the kind of the lack of the, it's mentioning the fact that somehow this P lambda is not a direct summand of m as an R module, right? So m P lambda plus, and this turns out to be direct sum if m is a positive depth, plus m of annihilator. Right? So this is the definition of congruence. Now, for those of you who have not seen it, if you want to get a sense of it, what is it in the case of m equal to R, right? Let me give an example. So when m is equal to, let's say, R, there's an example. So let's look at m equal to R, let's say equal to xy. I mean, this is the example everyone gives, okay? O squared. So that let's say x is congruent to y modulo pi to the n, right? Where pi is the uniformizer of O. Right? So then if you think about it, the congruence module, exactly. So in this case, the congruence module of R, right? This turns out to be O mod omega to the n. Right? So in some sense, measures congruence between different components of this ring. Right? So in some way, okay, so that's one intuition for why, one reason why one might consider it in a congruence module. Okay, and then the very nice theorem of Wiles-Diamond is that these two invariants, the order of phi lambda, this rank D, and psi lambda somehow interact with each other and give you a criterion for when R acts freely on M and when and at the same time R is a complete intersection. That's why it's very interesting to note that on R that there is no assumption besides this finite. So it has one component which is O, which could have some, it could be non-Cohen-Macaulay and some have higher dimensional components a priori, right? But somehow the beauty of the argument is that you get that in the end it is even a complete intersection. Okay, so what is the theorem? Then the theorem is So first of all, if you look at the length, I'm going to look at, instead of talking about cardinality, I'll just look at length as O modules, okay? So, and then let me assume M is a finite free O module. Okay, sorry. And R is an O algebra, okay, which I'm assuming. So now if you look at the length of O, length of phi lambda, right? And multiplied by this rank D, right? This D here. And first of all, one has the a priori inequality using some very simple fitting ideal argument, is that this is bigger than or equal to the length of O of psi lambda. Right? And equality, that's what this is some kind of easy thing. And then there is equality if and only if. If and only if M is a free R module and R is a complete intersection. There's a beautiful theorem. Okay, so so this was used by Wiles in the setup that you start with a situation where some deformation ring acts freely on some Ecker module, and then you verify this criterion or this kind of equality in some higher ramification situation by using, on the other hand, some simple arguments to control the cotangent space, some elementary arguments of Galois cohomology, but on the other hand, much more delicate arguments coming from Kendribbit and others to show that the congruence module is large enough, right? So a very delicate argument, and but once you have to verify this numerical equality, but once you verified it, it followed that you were in a perfect situation, right? So now, okay, now I'm almost out of time. Okay, so to state a theorem which kind of we proved, the idea is, okay, all this stood where it stood. Then Kissin and then various people then later kind of generalized the patching to become very, very flexible. Right, but the numerical criteria has lagged far behind. In fact, it has been an obstacle sometimes, and when people found ways to bypass it, like Taylor's, Ihara, Wiles, strict to relying upon Kissin's developments of the Wiles method. Right, so some of the people have always been obstructed in applying the numerical criterion for two reasons. First of all, it is very difficult to verify this criterion. There's this famous Ihara's lemma, which is kind of a roadblock. And okay, that's one thing. But secondly, I mean, Calegari-Geraghty, they generalize the patching method to situations where this numerical coincidence of G equal to R, right, which is a difference between Selmer and dimensions of Selmer and dual Selmer groups, fail. And still they had a development of the patching method to take care of the situation, which happens, for example, when you're interested in throwing R equal to T, in the situation where GQ, the Galois group of Q, is replaced by the Galois group of, let's say, QI, right? Imagine quadratic field, and you're looking at some sort of the modular object. It goes from a modular curve to some hyperbolic Riemann manifold, right? And so some of the patching method has been developed. But the numerical criterion one would have liked to develop, right? And we really need to develop it to get integral theorems of R equal to T, but that has been lacking. And so our idea to do this is to develop a higher dimensional version of this Diamond-Wiles criterion. So let me state that, okay? So let me state our commutative algebra result. Unfortunately, I may not be able to tell you how we apply it, okay? But let me at least end with some statement which we have proven, okay? Any questions? And I think in some sense, what is also interesting in our work is that we are defining some notion of congruence module in some higher dimension situation, which would be of interest even when you're not interested in patching and all that. Suppose you're working with some Hida-Hecke algebra and an augmentation of an O-valued point. What is the meaning of the congruence module, right? And we've defined it, at least assuming something, right? So you have to assume that the point is smooth on that eigenvariety or whatever, which is known in many situations. Okay, so let me just state this commutative algebra theorem, and then I'll tell you in a couple of lines how we apply it. Okay, so some of this is now going to work with right. So somehow we want to replace prove the same criterion, but with replacing having some higher dimensions. Okay, so I have to define the right category of rings. Right, so I'm going to define this category of rings COR, right? So these are going to be complete noether. I mean, actually, they're pairs of rings with an augmentation, but okay. So these are so this consists of pairs R lambda, right? Where R is a complete noether in local ring, O algebra, CP or ZL or something. Okay, and lambda is a map from R to O. And what you assume is that when you localize R as the kernel of lambda, let P lambda equal to kernel of lambda. Right? When you localize R at P lambda, then you get a regular local ring, right? So you get a regular local ring of dimension, let's say R. For example, the Wiles-Diamond case corresponds to R equal to 0, right? It's a regular local ring of dimension 0. So it's a field. So regular local ring of dimension R. And of course, I need not say put R, but this R is going to play a role in the kind of modules I consider over this. Okay, so this is a regular local ring of dimension R. So note that the R equal to 0 case is the earlier situation. Because of my remark that the finiteness of the cotangent space is related to the localization at the kernel being a field, I mean the fraction field of O. Okay, so that's my ring. And what is the module? And somehow this ring R is in application. There's going to be some version of this patched R infinity, right? So somehow that's going to be the thing. And this lambda is a smooth point of this thing. Okay. And this, okay. So now in this situation, I have a module M. But now my depth condition is going to be adapted to R. Right? I'm going to look at modules, finitely generated R modules with depth of M as an R module bigger than or equal to R plus 1. Okay, so this is my category of rings with augmentation, right? Which is smooth at that augmentation of and the localization of dimension R. Okay, and then my modules, the module M's I consider are going to be finitely generated R modules of depth basically equal. I'm just saying greater than or equal to. So that the depth of R equal to R plus 1, or you can say greater than. Right? So that's the situation. And now I want to generalize all these things. I want to generalize the cotangent space. I want to generalize the cotangent space exists, but I want to extract from it what I want, right? So then if you look at per p lambda, which is the kernel upon p lambda squared, right? This because of the smoothness assumption is just as an O module. It's a finitely generated O module. It's from the form OR, right? So rank R is an O module, but plus torsion, and the torsion is all important. Okay? Plus the torsion, okay? So which I'm going to call phi lambda.
But the depth to be equal R plus 1 or greater than?
You can put it equal to, a greater than equal to, then it's forced to be equal. It's the same. Okay, so plus phi lambda, so this is just some finite abelian group. And this is the phi lambda which occurred here, right? In this case, the entire cotangent space was finite. And okay, so that's kind of easy enough, right? So that's the cotangent space. And sometimes if you think about duality or something, maybe this is related to something like the dual Fermat group, right? Or some situation of some ordinary kind of situation. Anyway, but anyway, just computed algebra, there's just some, okay, we just separate out the torsion part. And
sorry,
then,
Shekhar, what does the check on the O mean?
this is R.
Oh, R, sorry, okay.
The smooth point, right? So it has to be the generic rank is K, is the rank of it is an O module is R, the same R. And okay, so okay, so phi lambda I have defined them. It's just the torsion part of this cotangent space. I want to define psi lambda. Right now, for psi lambda, I'll tell you what the definition is. So psi lambda m. Right, in each of the in the first case also it was a cyclic O module of finite cyclic O module. Again, it's only a cyclic finite O module, cyclic module. Right, what is it? It's the co-kernel of the map from X. Right, so the R equal to 0 was this Hom definition we used. Okay, so X R as everything in the category of R modules from O to M, right, to X R of O M tensor O. Except as before, you pass to the torsion free quotient. The co-kernel of this map is my congruence module. It turns out that because of these assumptions, that in particular this assumption that it's smooth at this point, that this thing is a finite or is a O module, a cyclic O module of finite type, of finite rank, of finite order, right? So co-kernel is this is right. Anyway, so if you just recall what we did earlier, the R equal to 0 case is exactly what happened in the diamond criterion, right? It was because X0 is just Hom. It was Hom OM to Hom O M tensor O, but passing through the torsion free part quotient. This is the maximal torsion free quotient. Okay. Any questions about this? So just replacing R0 to R, and then the generalization of the Wiles-Diamond criterion is right, there's a small kind of wrinkle. When one doesn't get freeness, one gets some direct summand property. Okay, I forgot to state some key property in the Wiles-Diamond thing. That one assumes that the rank, okay, in the Wiles-Diamond, let me go back, right? The rank of M, let's say as an O module, is less than equal to, right? The rank which you know dominates all the other ranks, right? So the rank of M as an O module is less than equal to D times the rank of O. And okay, you can say it in different ways. The rank of O of the image of R, let's say in image of R is the endomorphisms of M. Right. Anyway, there's some condition that somehow, I mean, there's some generic, and sometimes intuitively you can think of the fact that to tensor M with QL or QP, that should be free over the image of R, right? So somehow there's some kind of condition or controlling what's happening at the other generic points, right? So that somehow that was part of the criteria which I forgot to state. Okay, and sometimes it's a good thing to forget to say because our part of the thing forgets some part of that, right? And sometimes one of the key steps is to see what happens if you don't have this condition, right? Even in the Wiles-Diamond situation, if you look carefully, forensically at Diamond's proof, what you see is that you get a statement, right? And that statement is the one we generalize. Okay, so the statement here is, okay, so again, we have this new numerical equality. We always have, and this uses the positive depth, this depth condition. We always have that the length of O is a phi lambda times D, right? What is D now? I should also say what D is. So now another thing you can observe is that if you localize M at P lambda, this of course becomes a R P lambda module, and because of the condition, right? Again, you outlined the books. Once the regular local ring, and this is of depth at least equal to R, right? This is a free R module, right? It's free. I outlined the books. And again, so you can associate a rank to it. So therefore, P lambda is equal to, just as before, RP lambda to the D, right? For some D, and that D plays a role. Okay, so now we always have that this thing dominates the length of the congruence module. And with equality happens if and only if R is a complete intersection and M has a free direct summand of rank D, right? And M is equal to R to the D plus N, where the localization of N at P lambda is equal to 0. Right? So somehow it doesn't see lambda, right? Somehow it's okay. So this is the new commutative algebra. So it's just a generalized, it's a development of the Wiles-Diamond criterion to higher dimensions. I feel that even the definition of the congruence module is something of interesting thing to do, right? Irrespective of applications to patching, but I think it does have relations to L functions. We have not done that, right? But just when inspired by he does work, one would think that this congruence module also plays a role somewhere in that theory. And on the other hand, it fits perfectly into trying to use it for what? Patching, for proving R equal to T theorem, because you get a freeness. You get a direct summand property, right? And now what is one of the key things about being a direct summand? So the property of faithfulness of M as an R module is not preserved by passing on quotients, right? But on the other hand, the property of being direct summand is preserved when you pass to quotients. Because you imagine that this is being applied to some infinite situation, and you want to descend to reality by going modulo some variables, right? Relations, right? S1 up to S1. Now, I'm doing now. I think Morse code. I mean, I'm not telling exactly what's happening. So you have some patch situation where you reduce something like this, right? But you want to descend, when this is some patch, you descend to some actual situation, but then this property is preserved, right? So you get that M is equal to R to the D plus some N, right? And the main thing, one of the things you care about is that that M is a faithful R module, which will be preserved, right? So that somehow the direct summand property is replaces freeness. Again, I mean, if you have this second condition, again, you can get freeness, right? But it's that second condition of generic ranks being kind of bounded by the generic ranks documentation you start from is a very difficult condition to verify in practice. So it's good to have a criterion which doesn't operate. Okay, and now the last is, let me say, the application is the following. Right? So you consider GL2 of K imaginary quadratic field. Right, consider some kind of U an open compact subgroup of, right? Look at some congruent subgroup SL2 OK. Finite part of the depth, right? And then you look at the corresponding symmetric manifold. You look at XU equal to GL2 AK modulo U, U infinity, some compact thing, modulo the diagonal, right? And now you want to replace the modular curve with this manifold, right? It's going to be, for example, if K is some imaginary quadratic field, this is going to be some disjoint union of quotients of hyperbolic free space. Right? And one wants to prove an R equal to T theorem in this situation. So this thing has applications. So you then have some Hecke algebra acting upon the homology. Let's say H1 of XU. Right? And you'll be interested in some maximal ideas of the Hecke algebra. Now, of course, you're going to rely on deep work of Scholzer to say that there is, or at least even refinements, which I don't know whether they are actually proven, but one expects, right? One expects that to be a map from R to T. So here you'll be in a situation where you're in a map from R to T. Right? Known methods till now proved an isomorphism of R equal to T after inverting P or L, whatever the thing is. Our theorems throw R equal to T on the nose, right? And the interest of this is this T is typically, it could be just purely torsion, for example. It often happens, right? T, this homology is totally torsion. Because the difference between the Wiles situation of the modular curve and this is that this has homology in several degrees. In this case, H1 and H2, right? And so, because I mean, for various reasons, this might be all torsion, could be have lots of torsion. Our work right? In the minimal case, somehow when we do not have extra ramification, the patching method has been developed by Calegari-Geraghty to prove an R equal to T theorem in the minimal case without inverting P. But now because of our method, we get, so R phi equal to T, isomorphic to T phi follows from Calegari-Geraghty. It is the strategy, and we are just now, this is a rather, I'm reporting on this work at a preliminary stage, we're still writing up. I mean, so just now we just want to have a proof of concept. So at least assuming reasonable conjectures, one wants everything, okay? So like what Calegari-Geraghty did in the beginning. So on the other hand, to get R sigma equal to T sigma was not possible by either Calegari-Geraghty's original method or developments of it, like in the 10 author paper, right? They always have to invert P. But here we get an integral R equal to T, and that's good because lots of torsion, right? Otherwise you lose torsion. So good, I think I'll overrun my time. So, okay, thanks.
In your application, this condition that the localization at P lambda be regular.
Yeah, it's in our applications, this would follow. Because we're going to apply it at infinity after patching, right? We have a lot of choice there because we really know what our infinity is because we just avoid the smooth points. Yeah, that's the other. I think the psychological difficulty of finding this generalization was that there was no augmentation to work with, but after you patch there is, yeah. And it may not be anything which bears any relation to reality, no modular form, but it doesn't matter.
Maybe you could have went very quickly on that little corner of the board in the application to, I guess, cohomology of a hyperbolic three-manifold.
Yeah.
Which direction are you going here? What's the application?
So the direction.
You start with the torsion class, and you're trying to make.
Yeah. So in some sense, I'm assuming the kind of the one direction which I'm assuming is that there's a surjective map from R sigma to T sigma. That of course is already a deep theorem of Scholzer, right?
Okay.
You need to attach Galois representations to torsion classes occurring in the. So that's there. But on the other, so the point is to prove that map is surjective. So any torsion Galois representation comes from a Heck algebra. So that's the direction in which we have to. So a torsion version of Langlands of this.
Yeah. But the point is, you're saying they had to invert P.
Because they were, if you're interested in proving
then the torsion might be killed by that.
Yeah.
That's what you're saying. And you'll avoid that. Yeah, okay.
Because, for example, the developments of these methods, they were focused on a p-adic Galois representation. For that, proving R equal to T after inverting P is fine. But if you're interested really in finer statements of integral.
Yeah, okay. Very nice.
That was in some sense not the original motivation of our work. The original motivation of our work was to define congruence modules for higher, kind of some eigenvariety situation, right? And try to imitate the strategy of Wiles to prove smoothness of classical points on eigenvarieties. But for that, we needed a definition of a congruence module, right? At least to begin with. I mean, this thing falls short of that. But what it does fulfill is proving R equal to T, right? But there is there are questions if we thought about this in the setting of completed cohomology, like he does ordinary Heck algebra, which are interesting.
If you have a classical point and you do this patching in two different ways, will the resulting congruence modules be the same?
Sorry. So you could choose a classical point and look at the augmentation at that coming from that point. Is that what you're saying?
Yeah. Are these modules you define going to be independent of the way you do patching in that case?
No, I think these modules are some creation of, there's some artifice, right? Yeah.
So you don't expect to be able to see this congruence module in the space of automorphic form somehow?
Yeah, no. But if you do it in the situation of completed cohomology, in which case then you go on one. These are then things which are
that's some sort of specific way of doing patching.
Yeah, look, on some level, I think the cotangent space is going to be a local thing. It's only going to depend on the augmentation and the local deformation rings are infinity. And so since the congruence module equals the cotangent space, I think that will force it to be independent of patching. Right, because it will be determined by the kind of local properties of the representation you started with.
Yeah, I think we have some hope that if you have a classical point, like Akshay was suggesting, then we in fact can promote this in the applications, we can promote this direct summand property to actually showing it's a free R module by playing some game with components and so on. So there might be some advantage to have a actual classical point because one can use classical multiplicity one for automorphic forms to somehow say something. But that's something different.
Are there any more questions? I have a question. So how do you expect, or do you have any precise ideas about how you would expect these congruence modules to be related to L functions?
Maybe some periodical function. I mean, yeah, periodical functions. And I mean, how does it actually show up in practice? These 5 lambdas and so on. Suppose you're looking at a form F and you're looking at some Galois cohomology, except that the condition at P and the prime P or L order is relaxed, right? It's to be rather than being finite flat, it's ordinary or something. Then it's then the cotangent, then the kind of the Galois cohomology group, or at least some dual of it or something, anyway, is going to have some free part or some divisible part plus some finite part. Right, and in some sense that's what we are after, that finite part and its relation to L values and congruence modules. I think that this might be part of such a story. So I don't know, some periodical function, or I have no idea. I mean, this is some speculation, but we do think that it has some, it might fit. We also have an interpretation in terms of the commutative algebra, because for Hida, for his formulas, the L value has some relation with Peterson inner products, right? So there's some inner product situation thing which matters. So here also you can do this commutative algebra does, the congruence module, just as in the R equal to 0 case, can be interpreted using duality, right? Which might be some interesting thing for such application. So there is some inner product in this, which notices this congruence module.
So
yeah.
Continue this a bit. So the primes which support the congruence model, the classical, the Hida situation, they appear in the value at 1 of the adjoint L function.
Yeah.
And there, that's where you're dividing by the Peterson inner product to make that algebraic. And
yeah.
So in this higher dimensional situation, what is even the guess for what L function would this be related to? If you take the Bianchi situation, there again you can talk with the L1 adjoint. So that I suppose Eric Urban's generalization of Hida's that theorem.
Yeah, I mean, I've not thought about this. I mean, I've thought about it from the Galois cohomology point of view, which was in part of the motivation for this, because one wanted to have this generalize this argument of Wiles about controlling the Galois cohomology by using this auxiliary primes argument and using change of congruence module to the cotangent spaces. But I have not thought about the L function. But I think I'm sure there's a story to do it. In fact, that was part of a motivation, because I think Hida has in fact considered higher dimensional congruence modules, but he doesn't use them attached to an O-valued point. He'll look at a component of his algebra, in which case again you can use the X0 Hom definition, right? Because then somehow it's the same situation. Here the tricky part is that you're looking at an augmentation to a rather small ring O, right? I mean, this is a very high dimensional ring. So there's a mismatch in dimension, which is kind of accounted for by having to look at this higher X. Right, with some X0 generalization of considering higher dimensional things, but looking at augmentations also to higher dimensional things have been considered by Hida. In this, I think I will look too carefully at this paper. There is something like that. And that has some relation to L values of his modular form, the lambda-adic module. I think Chris maybe knows this story much better than I do.
Are there any more questions? Okay, well then let's thank Chandrashekhar.